Okay, so that is major losses. Major losses are denoted as the energy needed to get across a long straight section of pipe. There are other losses associated with pipe components, call them. Here's sort of the real stuff of piping systems, right? Because you could have a long straight section of pipe where this would have like a capital, I have capital L. Maybe to be very specific, I'll just say the subscript word. So this section itself would have a major head loss. Let's say it then goes into an actual valve to adjust the flow in the system. This also will have a loss just from getting from this point to this point. That is called a minor loss. And then let's say it even has another long straight section of pipe. Okay, there's another major loss. And then let's say it takes an elbow, right? It goes up to here. Here's 4, here's 5. This one also has a minor loss associated to it. And then more long straight sections of pipe. So you can kind of see it's all about getting these majors and these minors, the majors and the minors throughout your piping system. So I actually love the minor losses because it's a wonderful combination of like math and then experiment, because we just then define, well, the minor loss is just some number, k, times the velocity squared, 2g. So I'll write out the majors. This was to overcome the long straight sections of pipe, right? What was that equation? That was a friction factor. I'll put this on the side. Boom. Right? So we just say that the minors use this same velocity information, but now some number I have no way of actually like analytically deriving some energy loss through a valve or a ball valve or a T-junction or a threaded, right? That's just not going to work in math. So we just put it as a number. So then what you do to get this number is you'd run experiments. So you take your valve component. I think I have in the notes I had an elbow, but it doesn't really matter, right? So here. So this is also the process I'm trying to get fluid from point A to then point B, which is just simply across my piping component. Then you do an experiment, where the experiment is you vary velocities, right? And then what you measure is your head loss across it. So you're measuring pressures. So I always remind myself, right? Because it's really a pressure divided by a rho g. So that's why I had that extra credit, because like you have to measure pressure. I think there's some reason to it. So then what they do is you get a bunch of data points that have a correlation that go linearly up, right? Maybe they get a little crazy out here. Fit a best line. This are these minor loss coefficients. So that's how you get them. I would have loved to assign, maybe I still could, I would have loved to assign an experiment where you just do this at home, but you would need a way to measure velocity and a way to measure these. At home you'd have to be pretty good to actually do that at home. But it's just always cool that you just get this value of slope, right, from an experiment, and you just put all of the complications that come into having crazy geometry, right? Threadings and balls and fluid just moving all around it, but you just lump it into just some loss coefficient. And then these things end up being tabulated, right? So if you then sell some sort of piping component, right? So if I buy a valve, if I buy an elbow, right, they will come listed right? They'll come listed as a product with these things. So there are giant tables of different types or just average loss coefficients for piping coefficients. Or every time you buy one, sometimes you can look at a data sheet and you can actually figure out what the loss coefficient exactly is. Excuse me. So that's kind of the story, that we then now have these major losses and these minor losses. Again, these are majors due to the viscous forces. These are due to pipe components. So we can put all those together and then solve up sort of some real types of problems.